Welcome to day two of ValleyML's AI Expo for 2022. This is the virtual conference, and my name is David Wyatt. I'm the program chair for the virtual conference, as well as CTO of Pixel Display, a Silicon Valley startup company. Now, the people who've made it possible for us to be here include Habana, our platinum sponsor, Edge Impulse, who will be our next speaker, a gold sponsor, as well as FNX and Cognifiber, who are also gold speakers, and Applied Brain Research and Verta, who are our silver sponsors. So with that in mind, I'd like to jump straight in to introduce Jongboom. John is the co-founder and CTO of Edge Impulse, the leading development platform for embedded machine learning with over 100,000 projects. John's background as an embedded engineer led him to become an advocate for machine learning. John is always looking for new ways to gather intelligence from the real world. John has a real hardware credibility here. He's actually shipped real devices, worked on real technology down to the hardware level, including networking and microcontrollers. So he's one of these guys in the trenches just like me. We've been led to believe there's even a monument in San Francisco with his name on it. But either way, I'm looking forward to John's talk on building confidence in your AI models, in your ML models. And please remember, in the Hoover interface, you will be able to enter your questions during John's presentation. John will be in the background with the chair, myself, and able to answer your questions through the chat window. And then at the end of the presentation, there is a separate button that you have to click to enter the live Q&A session. Now this really is live, so you really do have to scroll down and click on that on time. It'll be on the session, but please don't make sure not to miss it and enjoy the presentation.
Hi and welcome to the last day of the ValleyML AI Expo. My name is Jongboom and I'm the co-founder and CTO at Gympulse. In the next 20 minutes, we're going to go over how you can build confidence in your ML models. So you can go from just your POC to actually having enough trust in that ML model that you created so you can actually deploy this on millions of devices. So at Gympulse, we're the leading development platform for machine learning on edge devices. Think of us as a development environment where you can bring your data, explore your data, and then see how machine learning can gather more intelligence from that. With an amazingly huge community, with over 100,000 projects created on Gympulse. We just reached that milestone 2 weeks ago. It's truly tremendous. And every day there's 300 new projects being created. And they vary from different sensor types. So from accelerometer data, gyroscope data, audio, radar, and some basic image classification problems. So as long as you have a problem that has sensor data in one end, and you can't write the control loop yourself, you know there's a correlation between the sensor data and the outcome, but it's just too complicated. 16,000 features per second, which you might get from your microphone. That's a lot of data to process yourself. Gympulse is the modeling place to go and do that. Now naturally, there's 100,000 projects. Lots of these are just proof of concepts. People throw in a few hundred audio files and they try to build a network and then it either works or it doesn't work. And that is absolutely amazing. But there's a big step between that point and the moment you actually go and deploy this on 1 million microphones all across the world, right? Our actual customers, they're building these self-contained models, monitoring real assets, probably in a harsh environment. Like it's not very easy if you have a deep embedded system to go update a model. These devices are actually spread around the world in the physical world. It's not as easy as something that runs in the cloud. So before you deploy, you want to actually build that confidence in that model already. And for me, the interesting part of all of this is that I think it's kind of overlooked, this idea of building confidence. But it's really easy to get bias in your model and thus have predictions that you can't actually trust anymore. And for me, this started very early, even before I started at Gympulse. It was still at ARM. In 2018, we were in Kenya at a conservatory deploying camera traps. And one of the camera traps actually said the next day, after we fetched the camera traps back from the conservatory, that a giraffe was spotted. And that was a bit weird because we talked with people in university, there's definitely no giraffes in the conservatory. But what happened? Well, we deployed a model that was actually trained on animals that we expected in Africa. And one of the animals in the conservatory was a llama that they imported from South America. And a neural network doesn't have an unknown state. It just looks at a llama and figures, okay, well, what is the closest thing in my training, kind of closest thing in my activations based on my training set that would actually activate here? And apparently it came up with, well, a long neck that has to be a giraffe. So this is kind of the funny side of things. There's also a dangerous side on machine learning models through adversarial attacks, right? Because a neural network doesn't have this unknown state, it just always reports something. I throw data in, it will always say one of these 4 classes or something it's trained on. It's actually possible to craft inputs that give you the desired outcome. So adversarial attacks are a way of actually tricking neural networks in the field. And this is actually the same problem as we have on the previous slide, right? If we don't know the input space or what our neural network is good at, how can we actually trust it? If we don't have a state of, hey, maybe there's an adversarial attack being crafted here to activate me, how do we actually counter that? This is my kid. When he was 1 year old, he started reading this Strengthening Deep Neural Networks book already, so he'll actually be prepared. And I hope you guys are too, about 15 minutes, in 15 minutes after his talk is done. So in essence, these 2 things for me boil down to the same point. We want to know what the strong and weak points of a model are, and we want to know when our neural network can't be trusted. Because that's the moment that I want to have an escape route and say, actually, I don't know what I'm looking at, but flag this, or actually don't operate based on the result of the network. So here's 3 things that I think can help counter that. The first one is just go build confidence in your data. Your model is as good as the data in it. And unfortunately, lots of the data sets that we see on a daily basis, customer data sets, yeah, but also kind of gold standard community data sets, are relatively bad. For example, if you want to build a person detector, your first response might be, well, I'm going to grab the Coco data set. There's lots of pictures of people in there, and I'm going to use that to train a model. But already in the first 10 images that I was looking through in Coco, I found this. Apparently this is tagged as a person. It's not true. Same in Common Voice, a pretty big data set of keywords in a variety of languages that's used a lot in benchmarking performance of small neural networks. One of the first examples that I saw here was yes, and this is just noise. And no matter how much engineering you're going to do on your neural network architecture, if the data that goes into it is wrong or mislabeled, you're never going to get a good result. Sometimes it is very clear, right? You can look at it. Sometimes it's less clear cut. If you look at a wearable manufacturer and you want to do sleep stage prediction on the wearable, you need to get reference sleep stages first, right? You need to know, was at this point someone in REM sleep? Because only after that fact you can actually train a model. So the way that these wearable health customers do this is that they go, for example, to a sleep lab. So someone sleeps with all these pads on their head. Based on that, they derive the sleep stages, and that's what then being used as labels. And then from there, you train a model on the actual wearable data. That might be that the research lab actually uploads the wrong file, maybe from the wrong participant. And if you just blindly trust that, now all of a sudden you have incorrect labels, and these are super hard to identify in your dataset. If you don't catch this early on, your dataset is going to be screwed forever, and you're never going to get the actual accuracy numbers that you really want. So how do we do that? Well, for relatively okay data, so images, audio, and whatnot, we've built a data explorer. The data explorer is pretty cool. It's a one view overview of your complete data set. And rather than using normal dimensionality reduction, we used your neural network, the embeddings from your neural network. So we cut off the last layer of the network where you do classification. We take the embeddings of the network and we use that before dimensionality reduction. And what that gives you is, well, a 2D overview of all your data, but sort of how the neural network would see it, right? So this is the last step just before it says, oh, this was noise, this was yes, this was no. And through that, you can very easily spot junk samples. So this is yes, but it's actually clustered in the noise cluster, and that's actually, it's not correct, it's actually noise, so misclassified, mislabeled. You can also use it to actually label data really quickly, which is a really nice benefit, right? Here's a gray cluster inside the noise cluster. This is most likely also noise. So really quick to label that. So the way that we do that, and this is a really cool trick, I think that more people should use it, is if you use normal dimensionality reduction, TSNE, PCA, then there's no inherent structure in the data, right? You just take the data at face value. If you throw an image through PCA, it just looks at the pixel values. But if we throw it through a neural network first, even if it's just pre-trained mobile net, the embeddings, so just before the last classification layer, it has learned about shapes and color and contrast and whatnot, all the stuff that you do normally in a neural network. So once we throw these embeddings through a dimensionality reduction algorithm, we get a much better overview, stuff that really nicely separates, because we're sort of having a debug view into the neural network. Really, really cool. So you can use a pre-trained network for this, like, pre-trained version of a keyword spotter based on common voice, or a pre-trained mobile net. But you can also use your own network. So label a few items, then throw the rest of your unlabeled data through and see if there's new clusters appearing, etc. So this goes better fast. On the more complex case, like the wearable health case, just really low-tech solutions, like just checklists, are already super powerful. Just stuff like, oh, actually, is the wearable data here? Do we have the EEG data? Do they actually start within 2 hours? Does the time zone match? And last one that we found is incredibly useful is try to find correlation between two devices. So, for example, in the ECG, EEG, like the pads you have in your head, typically you also put a clip on your finger to do activity measurements, basically an accelerometer. If there's also an accelerometer on your wearable, just plot the two graphs over each other and see if there's correlation. If there's not, maybe you're looking at the wrong files, or maybe something else was wrong. And you can also use this to time sync stuff. So here's actually an overview of one night of sleep, and you see that this is actually the same person, right? This is peaks all at the same point. But we also see that the red line is a bit earlier than the other, so we actually need to shift the blue data a little bit to have perfect overlap. So a really quick check of actually building some more confidence in your model. Step 2 is realistic testing. An accuracy number is, you can't trust it. Like, what does it even say? Like, if my model is 90% accurate, do I trust it? Yes or no? Of course not. There's no information in that. So one problem there is that if you look at the accuracy in a test set, even if you separate it out completely, your data in your test set typically is already really highly processed, right? You always split it up in nice windows. And it also doesn't capture application level details, right? So you do one window at a time, but what if you actually have, little overlapping windows, etc.? That's stuff that is kind of missed. And I also, and this is something that I probably go into debate with the real data scientists, is I would like to have information about what samples are misclassified. Because maybe I actually realize, well, there's music playing in all of these ones where we miss classification. So one thing we've learned from customers going through Alexa certification is that they do something better. So they test on realistic samples. So they put your device in a room for an hour, 24 hours, and they just write down how often did your device activate when it shouldn't, so when it didn't hear Hey Alexa, and how many times did you miss an event. And based on that, you get the false activation rate and the false reject rate. And those are really valuable stuff. So this is something that we actually try to mimic. Upload 24 hours of annotated data. We'll tell you what the false reject and false activation rates are. And from that, we can also start understanding the impact of post-processing. So we might say, for keyword spotting, we actually want a noise gate. Like, we want noise, keyword, noise. That is some application logic, right? It's not part of your machine learning design, but still really useful because it's gonna affect your false reject and false activation rates directly. So we have about 100 of these kind of post-processing ones. So there's also like, what is the threshold for a certain class should be? How long ago should it be that we heard a previous keyword before we trigger again? Like those rules. So we can take all of those rules and just test it out over the 24 hours of data. And from that, we'll give you this Pareto curve, and you can choose what you want to optimize for the false reject or for the false activation rate. Because if you have a keyword spotting model, you have a smart speaker, it's fine if it sometimes misses an event. Whatever, there's music playing or you talk over it a little bit stuff, you can just redo that. You can say, hey Alexa again. But if you have a fall detection system and you miss someone actually falling, that's really, really bad. So allowing kind of this check of like what is important for your model, typically balanced, right? Or actually I need to be super sensitive. That is really, really key, and we kind of try to plot that really quickly. And then the last thing is that we want to add some layers of defense, right? So this kind of comes back to the first 2 points that I made around the llama and the giraffe and the adversarial attacks. Don't trust the neural network. Like, even if we built everything that we did before, we have perfect confidence in our data set, we have perfect confidence in how well our model actually performs, not just looking at accuracy numbers. Let's also add a second layer of defense. So how we've done that traditionally is by deploying a second learning block, an anomaly detection block. So let's train a secondary model that doesn't need to learn how to classify data, but it just needs to know what is normal. Basically, the question that it needs to answer is, okay, here's a new sample. Did this look something like my data in my training set? Yes or no? So the way we do that is we just take all your data, we strip the labels off, and then we throw that through a clustering or a Gaussian mixture model. And then when new data comes in, we compare that to the model. And if it deviates too far, so it's outside of a cluster, or it deviates too far from the peaks in our GMM, then we don't trust that network. So here at the bottom, you'll actually see some data that is an anomaly. So it's really far outside of these clusters. We don't trust the neural network at this point. It's too far outside of our normal curve. To do that, you typically need to do some feature engineering though. So this works really well for normal sensor data. For example, if you know that you have a fan and that fan is on or off, well, I can look at the typical frequency. Here, the frequency between around 34 Hertz is apparently the normal spin speed. I can train on that frequency as the input for my clustering algorithm. And then when something starts happening, all of a sudden I don't see the peak at 34 Hertz anymore. And naturally we do this on multiple features at the same time. I know that is an anomaly. So that's relatively easy. And you can just start that by just training a binary classifier, just off versus normal, to get these interesting features. What classifies normal versus off, and then using that to train that clustering algorithm. Really straightforward. The cool part is that we can also do this on much higher resolution data by again using these embeddings. So just like we did it on the Data Explorer, we can now take a neural network, generate embeddings, and then take those embeddings again into an anomaly detection block. And now it works for high res data too. So here's an example from my house. On my left, I have photos of my lamp. On the right, I have photos of my plant, and I threw this through MobileNet. I took the embeddings. And if I add an unseen plant, so something that is the plant but has never been in my training set, it shows up nicely in a cluster. But then when I throw in a photo of my piano, all of a sudden it goes to this empty void. And that is actually a really good indication this is an anomaly. It's something that we have not seen before, so we shouldn't trust the network if the network is just trained on lamps versus plants. The funny thing actually is that adding a little bit of spare capacity in your network helps, because then it can kind of collapse. You can kind of know when you hit a random state in a network, that is an indication that an anomaly has happened or something you haven't seen. And then the last is also think about on-device calibration, right? An anomaly detection block or anomaly detection model learns what is normal for your complete data set. But what is running on the device itself in the field might be special for that place. For example, if you have a bridge monitoring case, actual customer case, your whole full data set has all kinds of stuff happening on bridges, including trains running over them. So you have an accelerometer model that monitors vibration on that bridge. But if you now deploy that device on a bridge where no trains are running, you kind of want to exclude the train signature from this point. So what we do here is that we say, well, the first time we deploy this device, it goes into calibration mode. And it learns kind of what a normal position on the anomaly curve is for that device. And after that, when we go into classification mode, if we see something that's not tagged as an anomaly, but it's still outside of the normal means for this device, we can still flag it as, hey, something weird is going on. Might be sensor, might be something wrong with the sensor, might be something else that happened on that device. So here's a really quick demo of that running on a Cortex-M4 microcontroller. This can be done super efficiently. So here is me, and we just have a device on my desk. and it's just trained on gestures, like waving up and down, snake over my desk, etc. So here we go into calibration mode. So it's been laying idly on my desk, and then I move it up and down. And those two are the only two things that this device should have seen. So the moment that we say we're done with calibration mode, we now go train, kind of fine tune our clustering algorithm. And now we know what is normal for this device. So idly on my desk is okay. Moving it up and down is also going to be okay. But then waving, which was something that's actually in a training set. So for a normal device, this is fine. We've now learned that that is actually an anomaly for our device. And this is so small, this can actually be done on device, even on Cortex and microcontrollers. So if this is something that you're interested in, this is not published yet. So we're currently looking at this with the first customers. If this is something that interests you, go ping me after this talk, and happy to walk you through kind of what that enables on real devices. So yeah, that was a lot of information, I hope. Here's my little recap. Kind of what are the 3 takeaways for today on this last day of the AI Expo. If there's one thing to take away is don't trust neural networks. Yes, they are amazing, but they lack a fundamental kind of basic, I don't know what I'm looking at, please disregard whatever I've said, unfortunately. Don't trust them. Always build a second layer of defense. You know, understand the strong and weak points of your models. Know the places where your model fails, right? If you see 99% accuracy, is that enough? Probably not. Understand what is 1% is and see what you can do to counter that. Yeah, the last part, sorry, it's still a little kicker to Gympulse. Gympulse, awesome product. We are thinking about exactly these problems. We're embedded engineers that understand signals and want to use machine learning to have a better understanding of the world. So all the stuff that you've seen in the past 20 minutes is already integrated into a Gympulse. So if this is something that you care about, go build your next ML model on that. And here's a graph of projects created over the last 2.5 years. I would love for you to create one of the 300 new projects today. You can do so for free at gympulse.com. Thank you.
Welcome. So we have Jan online ready to answer your questions.
Thanks, David.
It's good to have you here. Tell me a little bit more about what are the key things that drive you at the edge? I know for sure compute power is going to be one of them. How about size, other things that are really important at the edge?
Size and power as well. Like if you look at where really tiny models are being deployed, in your health wearable, in like little cameras that are being placed, in microphones that are attached to steam pipes, and even on sensors that are attached to power lines. Power is always kind of the hardest thing to come by. It's really easy to just like plug a couple of batteries in, but it limits what you can do. It limits how much you can send to the cloud, but it also limits how much inferencing you do actually on the edge. Even if you have a very small model, if you continuously run inferencing over it, you're going to burn through your battery in a week. So we need to be smart about when we run, what triggers we actually use to go run a larger neural network. That's kind of the main consideration.
Okay, and so what is the secret to get in the smallest power possible, in the smallest power budget?
Yeah, so heavy duty cycling, that's one thing, and being smart about it. So for example, microphones, like the MEMS microphones that you have, a lot of them have some way of setting, hey, actually give me an interrupt when there's more than X decibel. So stuff where you can say, okay, well, we only fire if we're actually above 50 decibel, otherwise we're always asleep. And then if we don't have something where we actually need to be awake all the time, like we need to do detection on a leakage on a pipe, for example, it's fine if that's 10 seconds late. In that case, we say, okay, well, we're just going to sleep 99% of the time. We're going to wake up every 10 seconds, do one inference, and then go back to sleep. That's one way. And then the other way is say, well, we can go much deeper with specialized silicon. So if you use a general purpose MCU, well, then you have kind of the overhead of the general purpose MCU. So we've been working with Sentient, for example. They just said, well, we do one thing well, and that's audio. So they have an audio front end and a fixed neural network, but all laid out in silicon. And that's super easy. You just drive stuff through this all the time, and you can't really go lower than that. So if you need something always on, then that's a way to fix it. It's expensive if you need to spin your own silicon, but that's the lowest you can go.
Yeah, and you kind of touch on correlation finding in your talk. Can you maybe give us one story on that? And apologies, we've only got a minute left of the live Q&A, but see what you can hit on.
No problem. Yeah, so back in 2019, we started working with Aura. They make a sleep ring, and we were in Singapore, and we needed to know if the person sleeping in the sleep lab. So we were going to do sleep stage analysis on the ring,
Right.
and we needed correlation. That we needed to know if the person was in REM sleep or in deep sleep or in light sleep, whatnot. So you put a person in sleep lab, put pads on their head, and that's how you get your gold standard labels.
Right.
But how do you know if you're looking at the right person and if you're looking at the right time? So at the beginning, we did this idea of, okay, people clap twice at the beginning of your sleep and at the end of your sleep. Well, think about that. That is really hard to remember if the first thing you need to do after you wake up is clap again. So what we settled on, I think is still ingenious, is that we derive the heart rate on the ring. We derive the heart rate from your brain activity scan, and then we just overlay them. And if we see nice correlation on these, we know we're looking at the same person and start and enter correct.
Thank you.